Okay, welcome to the first of our review lessons, Regents Review Unit 1 and 2, and our focus is going to be on math, measurement, and matter. Recall that matter is anything that has mass and volume, which means it takes up space. And we can then classify matter. Can it be physically separated? Can you physically separate the matter? If yes, then we would say it is a mixture. If we can't physically separate it, then we say it is a pure substance. So let's look at the mixture side first. So if we can physically separate it, we know we can classify it as a mixture. And then is the composition of that mixture uniform, the same throughout, or is it non-uniform? So if it's uniform, we say it is homogeneous. And a most common example would be a solution. So for example, if you look at salt, if we dissolve salt in water, that is going to give us a uniform composition of salt dissolved in water, and that AQ, that aqueous designation, tells us that we have a homogeneous mixture. That's our solution. And if it's non-uniform, then we say it's a heterogeneous mixture. And a good example of that would be oil and water, or we can say some soil. If we classify matter and say that is not physically able to be separated, we would call it a pure substance. And there are two types of pure substances. We have an element which cannot be chemically broken down. The word decompose means broken down. And so example would be like Mg, or a diatomic element like H2. If it can be physically broken apart or decomposed, we call that a compound, which is two or more elements that are chemically combined. And this example here, if we have sodium chloride as a solid, we can then chemically decompose this by breaking it apart into sodium and chlorine. So breaking it back down into its individual elements. We also drew particle diagrams in this unit, and these are important throughout all our units. And so when we represent an element, it's going to be one type of circle for a monoatomic element, and for diatomic elements, it's going to be two circles, but they're the same color, either two non-filled-in circles or two filled-in circles. So in this case, we have two H's that are together, and that's why they are touching each other. There are 7 diatomic molecules or elements that we have to memorize, and this was the Brinkelhoff or Hofbrinkel. So we have the hydrogen, and then we really start at number 7, nitrogen, and we make or form a 7 here. So these are all our diatomics. So recall that when they are not in a compound form, we always find them combined with an identical partner. So in this case, 2 hydrogens together. A compound is 2 or more different elements that are chemically combined. So example would be HF. And we would represent that in our particle diagrams by having 2 different circles that are touching each other. Do not confuse that with the 2 circles that are the same. These are elements. These are the diatomic elements. So the real difference is elements are made of the same type of substance as we have here, and compounds are made of 2 or more different substances chemically combined. A mixture is when we have 2 or more different substances that are not chemically combined, and we show that by the fact that these things are not touching each other. So in this case here, this is a mixture of 2 elements. This element here, let's say this is magnesium, and this element here, let's say this one is zinc, and then a compound, and we can call that NaCl. So this is a mixture of 2 elements and a compound. Again, notice that they're not touching each other, and that's why it is a mixture. A mixture is just having 2 more different things in the same space at the same time. How do we separate mixtures? Recall we did a lab on this. We can filter. So filtration is like when you're making coffee. It gives us the ability to separate an insoluble, non-dissolvable solid from a liquid. So example that we did in class, we had sand and we had salt water. So we could separate the indissolvable or insoluble solid, the sand, from the salt water solution. So when we poured that through our filter paper, the sand, the solid, gets stuck in the filter paper, and then our aqueous solution would then go through and collect that in our flask. Distillation is used to physically separate 2 or more liquids that are based on their boiling point. Recall that all we did was we boiled, and the one that has the lower boiling point boils first, and then that vapor travels up the tube here and then goes through this condenser. It is cooled, and it turns back to a liquid, and then we could pull this away, and then the next one is going to boil, and so on and so forth. So we could do this for multiple substances as long as they have different boiling points. Recall our phases of matter. So solids are very compacted together. They have a definite shape, definite volume. They're still moving. They can vibrate in place. And then if we add heat, endothermic, then we melt that solid and we form a liquid. Notice the liquid is more spaced out. It has a definite volume, but it takes the shape of the container. The particles have a little bit more ability to move freely. And then if we continue to add heat, again endothermic, we get to boiling, and the particles have the least intermolecular forces of attraction here. In the gas phase, there is not a definite volume or a definite shape. The particles are always going to fill the container. So they have the most amount of movement, and they are the most spread out. And if we want to use words like entropy, gases have the most entropy. If we went from a solid directly to a gas, that is called sublimation. An example we talked about in class is carbon dioxide solid, which is dry ice, and it goes right from the solid phase right to the gas phase. And then if we cooled that substance, that would be deposition, going from the gas back to the solid. And so to cool it, that's an exothermic process. We're removing heat, taking heat away, and that's why it's cooling. So condensation and freezing are exothermic processes. We're taking away heat or removing heat. Talking about changes, we have two types of changes. We have a physical change. This is a change that does not change the chemical properties of the substance. So physical phase change. So phase changes are definitely physical changes. Boiling, melting, freezing. We're not changing the substance. So for example, if we have solid water we call ice, if we melt that or we boil that, it is still H2O. It's still made of the same things, has the same properties, chemical properties. We're just changing the phase of matter. Also cutting or ripping, dissolving, crystallization, these are all physical changes because we're not changing the substance. A chemical change is a reaction when we have a new substance being formed. And some key things to look for, some words are burning, rusting or oxidation, reacting, decomposing, breaking down, synthesizing, making, corrosion, again, things like rust. And so we see chemical reactions where we have one type of substance as a reactant and we have a new substance being formed. That's the key here. That is a chemical change. Moving on to significant figures. Sig figs are a way for us to determine the precision of the measurement, how precise it was. So for significant figures, the first thing you do is you're going to start counting at the first non-zero. So in this example here, I start counting at the 7 here. And I count 7, the 8, and the 9, so this has 3 sig figs. Second thing to remember is that any zeros that are trapped between non-zeros are always significant. So these two zeros here are significant because they're trapped between the 3 and the 6, which are non-zeros. So this has 4 sig figs. And then the last thing is the zeros trailing after the last non-zero, as indicated here, are only significant if there's a decimal point somewhere in the number. So for example, here we're going to start counting at the first non-zero, which is the 5, and we have 1, 2, and then 3, 4. These two zeros are significant because we have a decimal point present. In this example here, the 5 and the 6 are significant. These zeros are not because there's no decimal point present, so this only has 2 sig figs. For rounding, when we add or subtract, it's the same rule for sig figs. We're going to round to the least precise place value. If there's a decimal point, the least number after the decimal. So for example here, this is precise to the tens, hundredths, thousandths place, and this is precise to the tenths place. So our answer here is going to get rounded to then the tenths place. And so we'd round to 61.1. This 9 rounds this 0 up to a 1. Here, there's no decimal here, so this is actually precise to the ones place, and this is precise to the hundredth place. So our answer then, 10.5, is going to get rounded to the nearest ones place, which is going to be 11. Multiplication division, we're going to round the answer to the least number of significant figures in our values. So this one has 1, 2, 3, 4 sig figs. This has 1, 2, 3 sig figs. So we're going to round our answer then to the least precise, which is going to be 3 sig figs. So here is our answer from our calculator, and so we're going to round it to 324, which is 3 sig figs. Performing unit conversions, we're going to use Table C. Table C gives us a factor, and it's important to note that our base units, anything listed on Table D, so things like meter, liter, gram, etc., are going to be here, and they are 10 to the 0. So I would write that down in your notes. So I'd write 10 to the 0, and some examples are meter, liter, and gram. Some of your common base unit examples. And for the exam, you need to know how to convert from milli to a base unit, or from kilo to a base unit, and then vice versa. Okay, so if a unit is getting larger, for example, going from meter, which is a base unit 10 to the 0, to kilometer, which is 10 to the 3rd on my table, the number is going to get smaller because I'm going to have less of them because I have a larger unit. And then if I'm going from a small unit to a bigger unit to a smaller unit, then the number is going to get larger because I'm going to have more of those smaller units. So let's see an example. So the first thing you want to do is identify our factor. So the first one is millimeter. So I locate milli, and that's 10 to the minus 3. And then I want to go to meter, single letter, base unit, 10 to the 0. So the difference between my factors are -3 and 0 are 3. So I'm moving my decimal point 3 places. Now the question is, do I go left or right? So since we're going from a smaller unit to a larger unit, we're going to go to the left 3 places. The number is going to get smaller because I'm going to have less of those bigger units. So I move my decimal 1, 2, 3 places, and so I get an answer of 0.0235. For our temperature conversions, we have Table T, which gives us Kelvin equals Celsius plus 273. You need to memorize that freezing, also known as the melting point of water, is 0 degrees Celsius, and the boiling condensation point of water is going to be 100 degrees Celsius. That's something you need to memorize. For calculations, something like this would be a good example. What is the temperature in Celsius of an object that is 150 Kelvin? So you plug in your values. I plug in 150 for my Kelvin. I'm solving for degrees Celsius plus 273. So to isolate Celsius by itself, I subtract 273 from both sides, and I get an answer of negative 123 Celsius. Remember that we could have negative Celsius values. We cannot have negative Kelvin values. For density, density is also located on Table T, and that's mass over volume. Be careful, make sure you understand what they're asking you for. Are you solving for D? Are you solving for M or V? So in this case, what is the mass of an object with a density of 0.3456 grams per centimeter cubed and a volume of 112.4? So you plug in your values. So density is on the left. We're solving for M, our mass, and here's our volume. Set it over 1, cross multiply, and you're going to get 38.85 grams. Always do a check. Plug it back in, and then divide and see if you get this density. Also note that when we're comparing two substances, for example, box A and box B, box A is more dense. Why? In terms of the particle arrangement, which is a question they ask a lot, the particles are more compacted or closer together, and that's why it has a greater density. If they don't give you the density, you can look it up on Table S. So for example, the volume of an aluminum sample is 251 centimeters cubed. What is the mass? Well, we're missing two variables, but not really. If you go to Table S, you can see the density of aluminum is 2.70, and then you can plug in and solve. So don't forget you have this option on Table S. For percent error, we're using our calculation. The most common mistakes students make are putting it over the accepted value. they often sometimes put it over the measured value. So just make sure, go back and read the question and make sure that you are doing that appropriately. So for example, a student measures the mass of a volume of a sample of copper at room temperature. The mass is 48.9 grams, and the student is measuring that, and the volume is 5 cubic centimeters. The student then calculates the density. What is the percent error of the student's calculation? So we first figure out what was the student's calculated density, which is this. I look up the actual density on table S, which is this. And so it's measured, the student, the accepted, the actual. So measured minus accepted over the accepted, and don't forget times 100. And we get a 2.46% error. And lastly, calculating with scientific notation. We're using our calculator to put in these values. This times 10 to the 7, for example. You're going to type it in just like this, 5.44, and now we want to enter this exponent. So there's a button called Enter Exponent. On our calculators, it's the second function and then this EE. So you'd hit second function EE, enter the exponent, and then you enter that exponent, which in this case is 7. And then divide it by and do the second one. Make sure you're using parentheses around each of your values, and then you'll get an answer. And always go back and check your work with the calculator and make sure you didn't make a mistake.